is we look at rational functions, which are really just functions that can be written as a ratio of two polynomials. So a numerator polynomial and a denominator polynomial. These would be our rational functions or ratio functions. And so as we look at these, one key interest is going to be on just where the asymptotes lie. So we're going to start with this idea of vertical asymptotes. When we talk about a graph, these vertical asymptotes are these individual x values at which our graph might be undefined, okay? So when we talk about undefined, we usually are referring to things that are, taking a root of a negative, but also dividing by 0. So when we look at the domain of functions, this is a lot like we did in chapter 1 here. It says find the domain of the function, be sure to write the domain in interval notation. What we're really looking for are these values of our denominator polynomial, these values of x that cause our denominator polynomial to be equal to 0. So again, all we're really doing is looking for the zeros of the denominator here. If, we say our polynomial is x plus 1, that's our factor, well then the 0 is going to be x equals -1. What I want you to consider is that you would maybe want to draw a picture here. It means that at -1, we have a split here. So when we talk about what our domain looks like as a set of intervals, we say everything to the right of -1, everything to the left of -1, but not at -1. This is where we get this negative infinity to -1 in unity with -1 to infinity, and you'll notice that we're excluding the -1 here. So something like number 3 here, when you look at it, it's second degree. It just means that we should get 2 zeros here. That would factor into these, which would mean that we would have zeros at plus or minus 3. So again, if I were to draw a number line, we could just look at it this way. Here's -3 because I said so. Here's +3 because I said so. It's this idea that these are excluded. Well, then we're going to have all these intervals that exist in between, but not at positive and -3 here. So looking at these, we want to write them from left to right. It'd be negative infinity to -3 in unity with -3 to 3, and that's unified with 3 to infinity. So we're going to be looking at these domain restrictions, but also I want you to know that when we find the zeros of the denominator, those x values that cause your denominator to be 0, those are actually also the locations of your vertical asymptotes here. And so you'll notice that our domain that we write up here is kind of the counterpart to our vertical asymptotes. When we look down here, say at these, it says find all vertical and horizontal asymptotes of the graphs of the functions. If the graph has a slant asymptote, then give the linear equation. The slant asymptote, well, we're just going to start with the vertical asymptotes, and I want you to know that the vertical asymptotes are always occurring at the zeros of the denominator. So, for instance, on number 7 there, we say, well, if I factor the top and the bottom, it looks like this factors it, it's going to go here. What are the zeros of the denominator? If I set this equal to 0 and solve it, I get 0 twice. I get plus or minus 0. So, for whatever it's worth, my vertical asymptote is going to be at x equals 0, because when I plug in 0, I get undefined. Just like on number 8 here, what would be the 0 of my denominator? It would be positive 2. So my vertical asymptote is at 2. Essentially, what you're going to be doing is rolling through all of your denominators and finding the zeros, because these are going to be the locations of your vertical asymptotes. So for instance, on number 11 here, we kind of looked at x squared minus 9 a moment ago in the domain. We would say our vertical asymptotes occur at plus or minus 3, because those are the values that when I plug them in cause me to divide by 0. So you'll notice that the domain up here, I say what are all the x values we do use? It's kind of like the exact opposite when we talk about the vertical asymptotes. These are the x values we don't use. These are all the x values that are remaining once you remove the vertical asymptotes. So the only other thing we want to talk about is horizontal asymptote. Really quickly here, remember that if it's a situation like this, n of x over d of x, okay, we're going to say that there are 3 situations here. Horizontal asymptote occurs on the x-axis if degree, I can spell here, degree of n is less than that of d. So if the degree is smaller on top than it is on bottom, it's kind of like a proper fraction here. We're going to say it's the x-axis, or y equals 0. So this right here. When you look at number 7 here, I notice that the degree of the top is 0. It's a constant polynomial, and this is a quadratic polynomial. So because it's bottom heavy here, we're going to say that this x-axis is going to be our horizontal asymptote. So do we see any other instances where the degree is bigger on bottom than it is on top? I notice also on number 8 here. And so we're going to say y equals 0. So now, something like number 9 here, you'll notice that the degree of the top and the bottom are the same. Same thing on number 10, they are the same here. Even on number 12, they're the same on top and bottom. So what if we're going to say y equals the LC top over LC bottom. In other words, the leading coefficient of the top over the leading coefficient of the bottom, if degree of n is the same as that of d. So looking at, say, number 9 here, we'd say the leading coefficient on the top technically is -1, and the leading coefficient on the bottom technically is +1. So for my horizontal asymptote here, I would just simply write -1 over +1, or y equals -1. That's going to be the equation of our horizontal asymptote. Like number 10 here, we see the leading coefficient on the top is -5, leading coefficient on the bottom is -9. So we look at this, we get y equals -5 over -9, or 5/9 would be our horizontal asymptote. And then number 12 here, we would say that because the degrees are equal on top and bottom, we look at the leading coefficient on the top over the leading coefficient on the bottom, this would be y equals 4 over 1. Okay. So the last one here is just finding slant asymptotes. So number 3 is going to be, it's a slant. Slant if degree, oh come on, degree of the numerator is greater than that of d. So looking at number 11 here, it's third degree on top, second degree on bottom. What we essentially do then is we'll just long divide, and what we're looking for is the quotient. Okay, that's going to represent our slant asymptote equation. So whatever we get up here minus the remainder. So if we were to put this in, we'd have x cubed plus 0x squared plus 0x plus 0. And out here we'd have x squared minus 9. What can I take times x squared to get x cubed? I would take an x. X times x squared is x cubed. X times -9 is -9x. And again, we're going to wrap this up and subtract it all. I suppose we'll change these signs over. But essentially I get left with 9x plus 0. And what I want you to notice is that x squared is not going to go into 9x at the first. So this right here, whatever the quotient is, I don't care about the remainder, that represents our equation of our slant asymptote. So we've got to be able to find your asymptotes. If you can do that, we're going to put our graphs together really easily. Cheers.